10:30, so why don't we go ahead and get started here. Welcome to the session on technology adoption, causes and consequences, which almost assures that we will have some kind of technology glitch here as we go along. All three of our presenters are going to join us here on the big screen, and we are going to start with Bjoern Brey, and he's going to talk about the long-run gains from the early adoption of electricity. And Bjoern, go ahead and share your slides, and it's all yours.
Thanks a lot, Michael. I hope my internet connection won't be glitching immediately after you said so. I'm already struggling to find now my PDF file, even though we previously tried it. It just moved to some end of the Zoom, but I hope you can see it now. This paper is titled "The Long-Run Gains from the Early Adoption of Electricity," and kind of its main focus is on understanding how the adoption of a new technology really early on in its commercial use affects economic development within an advanced country. And the motivation for this comes kind of from the major observation that the timing and intensity of technology adoption is kind of crucial for the drastic divergence in incomes across countries. But we have much less understanding of what are the positive effects of new technologies early on within advanced economies that adopt those. So there's, like, for example, the solar paradox. So we really struggle to nail this down. And this leads me to three key empirical questions. Firstly, I want to look at, does the early adoption of a new technology lead to economic development? Secondly, do differences in economic activity persist over time as new technologies become adopted more widely? And thirdly, if this is indeed the case, what mechanism can explain this persistent divergence in economic activity? And to investigate this, I explored the geographical variation in the potential to produce electricity from water power across Switzerland, combined with some nice quick transitions in the way power is generated from water, as well as kind of transmitted later on. And to give you a bit more background on this historical setting, which I think is quite excellent to study the adoption of a new technology, the first key ingredient is that Switzerland is actually a major adopter of electricity in the late 19th century. So it's actually ahead of the United States in per capita generation of electricity by 1900. So there's this major adoption of a new technology going on. And this adoption is quasi-random across Switzerland because it relied on water power. And this is because Switzerland was so poor in natural resources that it was just unfeasible to import coal for electricity generation. It was just not economical. And I actually see that in the statistics, less than 1% of energy was generated from steam power, and the steam power was mostly to offset variations in the water level that was existing. So it was really driven by water power in Switzerland. And then finally, after 1900, there's like this rapid change from DC to AC technology, and you see really that like every 3 years, basically the transmission distance doubles. So after 1900, really you increase in the space of 6 years the transmission distance from tens of kilometers to several hundred kilometers. So there's a rapid expansion of this electricity grid, which makes access to electricity basically become universal across Switzerland. So this gives me a very neat setting where areas as good as randomly are exposed to electricity for only about 20 years. And that's really early at this kind of adoption of a new technology. So what do I find? Just to quickly summarize, I see that early electricity adoption led to economic development immediately at the end of the 19th century. And just to give you a sense for the magnitude of one standard deviation, higher exposure to electricity will lead to, is estimated to lead to a decline of 3 percentage points in the agricultural employment share, or vice versa, an increase in the manufacturing employment share. So this is quite sizable in effects. And what's remarkable is that this effect on structural transformation and also incomes, I can see, persists up to today. So these areas that had this shock with electrification very early on, they are still more industrialized today. And what seems to be the mechanism is not that it's technology itself. So I see that as the electricity grid has expanded, there's no difference anymore in the way electricity is used across districts, but rather it's that there's an immediate increase in the accumulation of human capital in these areas. There's also the setting up of secondary schooling. And I can also see that still today there's more innovation, which seems this key engine of why these areas continue to be more industrialized. In the way this is related to the remaining literature, so there's a lot of papers that I can cite here. So I cut obviously a lot because it's this kind of broad question that I'm interested in. But maybe three kind of areas here. So firstly, it relates to the literature on kind of electricity adoption, and in particular, a lot has been written about electrification in the United States. And what I think is nice in my case is that I really look at the earliest periods, really late 19th century, kind of the high point of the second industrial revolution. Electricity is this novel technology, and it seems to already, when it's like started to be commercially adopted, to be already having this economic impact, which is, I think, nice to see, because a lot has been written about, also by Mokri, about that this was really a key technology of the second industrial revolution. Then it relates to two recent papers on kind of the long-run effect of technology adoption, Franklin Talor, which looks at the steam engine in France in the middle of the 19th century, as well as Lewis and Severini, which look at rural electrification and the long-run effect it had in the United States. And those two papers really find very little impact in the long run, or even negative effects in the case of Franklin Talor. And I think it's a nice contrast that I see this positive effect, which might be explained by having a very different setting. So this is really first movers into this new technology, rather than kind of the laggards that adopt electricity a little bit later, or are like very invested into steam engine, a particular technology at the height of its use in about 1850, before it becomes obsolete. And then finally, it relates to kind of the literature, which looks at the effect of technology adoption and the accumulation of human capital. So now, just to give you an idea of what I'm doing, my empirical approach is as follows. I will estimate a set of regressions, which changes in the dependent variable over time t. So it's the change in my outcomes, in particular, the change in the employment share in agriculture, manufacturing, services, between 1880 to point t in time, which is up to today, across Swiss districts D. And I regress on this the initial adoption of electricity across districts D between 1880 and 1900, so the first 20 years of its commercial use. Then when I go further into the future, closer to today, I also include a control for later buildings of water power plants to disentangle the fact that there might be buildings later on which might try for the long run effect as well. And there's a lot of detail about this in the paper, that it's not a bad control, and that it's really picking up a particular effect here, which I don't have the time to go into, but it's actually a very important thing to narrow down this lasting effect to be only due to the first 20 years. And then I also control for initial characteristics in 1880, like, for example, altitude, longitude, latitude, population densities, agricultural employment share, education, initial water mills, and main economic regions that might lead to divergent developments as well here. And apart from like this term for later adoption of water power plants, it's really very similar to event study design, just that it's estimated with individual time periods here. Now there's obviously another kind of key threat to the identification, and that is that electrification is not random, and it might depend on other factors that are obviously not captured by these initial controls. And this could be, for example, that industrialization actually is happening, and this is what leads to higher electricity demand, which would be an upward bias. But in my case, it seems to be actually another feature, which is that in areas where there's large marginal gains from adopting electricity, actually there's kind of a coordination problem in building big water power plants, because people have their own water concessions that they want to use for generating some electricity for themselves. And this stops the building of big water power plants. And this is very well documented also in my historic data sources. So really what's happening is that there's a downward bias that areas that had the biggest gains, like, for example, Basel, they really struggled to build any big electricity power plants, even though they really wanted to use electricity at the time. And to deal with both of these issues, I instrument the change in electricity produced per person from 1880 to 1900 with a log water power potential per person. And this log water power potential per person comes from a survey of engineers at the time, which kind of maps the optimal location of water power plants, disregarding any economic activity that's already taking place or whether these water power plants would be viable. And this is basically the map. So the black dots are the optimal located water power plants, and the size is basically how much energy they could generate. So this is very much distributed across the whole of Switzerland, and it's not driven by only major rivers. So you have some big power plants that could be built along the Rhine, but most of this energy comes from rather small rivers all across Switzerland. And you also can see that the darker areas, there's more electricity adoption. There's a lot of potential usually in these places. And to like the obvious kind of issue that you might have in mind is that these features are, of course, relevant for other economic activity already pre-electricity adoption, or it might be related to some other things like transport, etc. There's again a lot of this in the paper, but I think one really clear, obvious thing that might be an issue here is that these features might be relevant for mechanical water mills, for the production of flour that are having a long-standing impact on industrialization. And this really doesn't seem to be the case. So on the x-axis is basically this water power potential across districts. And on the y-axis, you have in panel A, electricity adoption by 1900, and the use of mechanical water power by 1880. And it's quite clear that this water power potential is important for electricity adoptions, for generating electricity, but it's not important for actually mechanical water power. And this is because there's a drastic shift with this technology of electric turbines. Thanks a lot. Also the electric transmission technology in how much energy you can exploit. So these features, the features needed for mechanical water power and mechanical mills are very different from the ones later used for electricity generation. And these are really small features like bends in the river using certain types of pressure pipes to generate this electricity. Now the data to get to the end. I use like a very big, like 5-volume book series, which really depicts all the building and extension dates of water power plants in Switzerland, the types of energy they produce and what it's used for. And also it provides the map of potential water power plants that can be built across Switzerland to optimize energy generation for the whole country. I combine this with sectoral employment from 178 Swiss districts from the census between 1860 and 2011. And this kind of gives me the opportunity to study the effect of this electricity adoption in the long run. So these are basically the estimates of the effect of electricity adoption instrumented by this potential on the change in employment share in agriculture from 1880 up to 2011 for all these different periods in between as well. And beforehand, that's the kind of effect before electricity adoption on economic development, which doesn't seem to matter. So it's really the case that immediately as electricity becomes commercially adopted, there's a large decline in agricultural employment in these areas, while on the other hand, there's this change into employment in manufacturing, as well as some increase in services, which however converges in the long run. This is kind of like my key finding, and I also have similar evidence for GDP, not at the district level, which is very detailed, which I have 178, but at the cantonal level, and it seems that these areas also have an increase in income. And I can document that today districts still have higher incomes when they adopted electricity. So now what's the mechanism for this? So on the mechanisms that I can rule out, there's persistent differences in the use of electricity as early as 1920. So it seems that areas that are exposed to electricity early on are quickly becoming equal in their electricity use as the electricity grid spreads and other areas catch up in terms of using these new technologies. It's also not related to the extension of electricity generation, though that's not what's driving the effect. It's really chemical and textile industries, which are the main driver of this lasting industrial employment effect. And it's also not agglomeration costs. So in Switzerland, it's a very interesting context in comparison to the US. We have relatively little internal migration, and I really see that there's no migration into these areas from other parts of Switzerland, as well as of foreigners for the initial 20 years. There's a bit of an inflow of population later on, but it is relatively small and is not really a good explanation for this lasting effect. Instead, what's kind of the mechanisms that I can well document is that there's an immediate increase in human capital accumulation, in particular at the secondary level of education. So I really see that in military test scores, there's an increase in kind of math and general knowledge in the population. And this is the population from the district. So it's really people that went there to primary school. Sometimes they have to migrate for secondary schooling to another area, but it's really these local people that increase their human capital, and it's very complementary to the industrial growth that is going on. And also what's kind of interesting is that there seems to be a complementary adjustment in the infrastructure networks. So these places also have more railroad connection points and also more commuters into these areas by railroad. So there's some changes in the infrastructure networks because a lot of the economic growth actually happens in very initially rural and poor areas in Switzerland. So it's really that these get connected, and it kind of explains why even nowadays in Switzerland you have a lot of very competitive, internationally competitive firms in relatively rural areas, which you don't usually expect to be the case. So I think I'm pretty much out of time, so I'm not going to go into the main human capital finding, but this is really, you see that it's really happening in math and general knowledge, that there's this increase in secondary education where there's very little at the primary level of schooling. So it really seems to be also related. I have evidence that there's more secondary schools being established, and especially in terms of vocational training, which might be done by the municipalities in combination with the local employers. So just to conclude, electricity had a major impact on industrialization already in the late 19th century in Switzerland. So really, as soon as it became commercially introduced, it was economically important in driving local economic development. This economic effect of early adoption persists up to today. So this is quite remarkable, I think, especially in the context of an advanced country as rich as Switzerland. We would think that these effects would quickly disappear as the technology becomes widely adopted. And the main mechanism is, as far as I have the evidence collected, the evidence that I collected is likely increased human capital accumulation and also future innovation. Thank you very much.
Thank you very much, Bjoern. If you could stop sharing, our discussant is going to be Jeremy Atack. And let me see if I can get his slides up here.
Thank you. Well, as we have all heard, this is a really nice paper, really thorough, well developed. There's no point kind of my going over what its goals were because I think you clearly saw them. But I do have some comments, and rather than waste time on talking about things that you're not going to learn anything from me about, like IV strategies. The only thing you'd learn is how little I know about IV strategies, and so that's not going to be very useful. But from what I have picked up over the years, the paper checks all of the boxes regarding instrumental variables and causality. So I'm perfectly happy with that. Instead, what I want to talk about are some extensions and ideas that might be useful to the author in following up on this work. First of all, on the construction of the actual IV from this 1916 survey. It's somewhat opaque. There is a fairly lengthy appendix in the paper, and it does contain this very nice map to illustrate the point, which is from that survey. And you can see that there are a bunch of dots on here. The blue dots represent actual water power sites in use in 1914 or maybe 1916. It's 1914, I think, when the survey was actually taken. It's published in 1916. The red dots indicate the potential sites that the survey identified, and you can't really see it that clearly on this image, except if you look really closely, right in the center of the image, there is a red dot with a little gray center in it, and that is a site that required a dam in order to use the water power potential, and the dots indicate the amount of power that could be generated. So,
hey Jeremy.
Yeah.
Sorry to interrupt. Your slides aren't changing for those of us on Zoom.
Really?
Yeah. So we've had this trouble before, and I think you just need to stop the presentation and then start it again. Like stop your presentation mode.
You want me to? So stop my share, and then. Okay. Yeah. Are you now able to see the slide?
Yeah.
Yeah,
Good.
Beautiful. Thank you.
Nice work.
Sorry, well, you didn't miss much on the other. I wanted to skip to this one, which shows some of the underlying data that Bjoern reproduces in Appendix C, showing where his data comes from. But despite the presence of this map, you really don't know exactly what the raw data look like. And I wondered if one could go behind the curtain and use some GIS to look at what it was that was driving the coding of those places. For example, GIS uses a metric called ruggedness. The two popular measures of ruggedness are one developed by Riley in 1999. Another one is the vector. Drawing a blank on it. VRM, vector ruggedness measure. That's it. That was done by Sappington in 2009. They both basically use a digital elevation model in a 3x3 matrix, and they focus on the central box of that 3x3 matrix, and they look at the change in both elevation between the surrounding eight boxes, and also that would be the Riley measure, and the Sappington measure also looks at the change in angle, so that if you're in a teacup, as it were, the ruggedness of a teacup is different from the ruggedness of a slide. So it gives you variation that way. And I wondered if a digital elevation model might actually let you independently look at where these sites were located. Also, whether there was any data on river flow. Switzerland, as we know, is a small and rugged country. The map on the right is the one that Bjoern showed you. On the left, I just took the Wikipedia map kind of on the same scale and plugged it in there to remind people of the geography of how the Alps are in the southern part of the country, the northwest part of the country, the mountains there are the Jura, and then running up from, Lake Lucerne, up towards the northeast. That's kind of the central plateau in Switzerland. But we're talking about a small area here. In terms of the United States, Switzerland is about equal to Vermont and New Hampshire. Now, electricity is a general purpose technology. I particularly like this first quote here. The use of electric motors is now so general that it is difficult to name any industry, manufacturing or otherwise, to which it has not been applied. The effort cannot be fully apprehended as it is in its earlier stages, and that's from the US Census of 1905. This is from Jovanovic and Russo, looking at the transition between water and steam and over to electric power. And you can see how dramatic it is in the United States, but it's exactly the same that's going on in Switzerland, except Switzerland really didn't have that. Switzerland did not have that steam power to begin with. But I wonder if one couldn't also look at some of these same issues for the United States. In 1880, the US Census did a survey of water power in the United States. On the right-hand side, you see one of the maps that was produced in that census volume. And on the left-hand side, you see details about the use of rivers by particular firms and industries dotted along these rivers. So it might be possible to kind of do something similar to this using US data. And there is, in fact, a later survey that was done by the US Bureau of Corporations in 1912 that also looked at water power and electric power in the United States. It's a survey. Sorry, that image on the right there is not particularly good. It was on Hattie Trust, and that was about the best I could come up with at the time. But there are detailed data that are similar to what Bjoern uses for the United States, and I think it might be useful to think about expanding this to the rest of the world, particularly given that it is Switzerland and the United States, the two leaders. Anyway, this was a really nice paper, and I applaud the author. It's a magnificent piece of work. Thank you.
Thanks a lot, Jeremy. Really great comments. Very enjoyed them. Yeah, I don't think I want to go back in any. I think they're really great comments, and they really helped me in narrowing down now the paper, rewriting it, and also great ideas for the future, especially also with the great US census data that's now linked over time. I think there's a lot that can be done, hopefully. So thanks a lot. Very enjoyed your comment.
Okay, we have about 5 minutes for any questions, either here presently in Tucson or online. Do we have any questions? If anyone online has a question, you can just go ahead and unmute and ask it. Okay, it appears between the two of you, you have covered everything at this moment. This is one of the downsides of having people all over the world participating at one time. It does slow down the response rates a little bit. But let's go ahead and move on. So, Michela, are you ready for your presentation? We have another online presenter here.
Yes, sir.
Okay, so you can go ahead and share your screen and take away.
Okay, so hi everyone. Thank you very much for the organizer to putting together this very interesting panel and to face the challenges of having both people in person and on Zoom. I know it was a lot of work, so thank you so much for doing so. The paper that I'm going to present today is titled Technology Transfer and Early Industrial Development, and is joint work with BOLI. So the motivation of this research is that the international transfer of knowledge and technology are key elements for economic development. They've been widely used to push industrialization in developing countries, mostly through the diffusion of state-of-the-art capital goods, but also the dissemination of some specific know-how may have important effect on the industry establishment and subsequent expansion. Despite the importance of technology and knowledge transfer, however, little we know about their causal effect on early industrialization, mostly due to lack of long-term data and natural variation in the delivery of such interventions, but also because technology and knowledge transfer often occur simultaneously, and so it's hard to disentangle the separate effect of the two interventions. So to solve this issue, we turn to economic history, and specifically we use evidence from a unique historical episode, which is the Sino-Soviet alliance between 1950 and 1960. The alliance between Soviet Union and Communist China involved both military and economic cooperation, part of which was focused on the so-called 156 projects that were projects to build technologically advanced, large-scale, capital-intensive industrial facilities. These projects could be of two types. There were basic projects whose goal was duplicating old Soviet plants and transfer state-of-the-art Soviet machinery and equipment, and advanced projects that, on top of the basic components, also involved training for engineers for Chinese engineers and technicians, and technical assistants. Through this program, China received the best technology available in Soviet Union, that in some specific industries like like steel and iron was the best in the world. So in terms of data, we have collected all information on all the projects that have been approved between 1950 and 1957. And despite the iconical label of these projects was 156 and has persisted up to today, the projects that were eventually approved were 139. For plant in the steel industry, we were able to have yearly data from their balance sheets between 1949 and 2000. And for all the other industries, we have data in 1985 and between 1998 and 2013. In terms of identification, we use the fact that after project starts, most of them face some unexpected delays that were related to Soviet issues and not on project characteristics, and I will be more specific in a minute about this. And so when in 1960, the Sino-Soviet split meant the sudden cancellation of the technology transfer program, projects that experienced fewer delays had already received and retained the planned transfer, so either the basic or the advanced transfer, while projects that experienced more delays were completed by China alone using domestic technologies. And I will show that these two types of projects were very similar in terms of their observable characteristics and the characteristics of the provinces and the industries in which they were operating. We find three main results. So first, the advanced transfer receiving both Soviet physical capital and human capital had a large and persistent effect on firm performance. We document an increase in both output quantity and quality, and a gain in productivity of 52% over 40 years with respect to plants that were supposed to receive the advanced transfer but did not due to the delays. We also show that the plants that received the advanced transfer were the only one able to develop domestically new technologies when China was a closed economy, and this technology was used to replace Soviet capital that over time became obsolete. And when China opened up to international trade, these firms were relying dramatically less on foreign import and were exporting more. And finally, as the main goal of the program was to create large industrial facilities to push local industrial development, we measure spillovers effect. And what we find is that being close to advanced treated plants is associated to substantial productivity increase for firms that were horizontally or vertically related to treated plants. And since the late 1990s, this also implied a reallocation from state-owned to private-owned firms. So in the interest of time, let me skip the contribution to the literature and let me move to the overview of the talk. I will start giving more detail about the context that we are studied and our empirical strategy. Specifically, despite the cooperation between Soviet Union and China was described as a rosy friendship, on the ground, the implementation of the technology transfer program faced many delays. Very often, machinery, equipment, and design arrived to start operation later than planned for a bunch of different reasons. So first of all, there were constraints on the Soviet production capacity. Soviet Union didn't have the equipment with the machinery in stock. They had to produce as needed. And so if there were some issues with the equipment used in the Soviet factory, this, of course, had a priority relative to shipping the equipment to China. And so these shipments were delayed. Similarly, Soviet Union had a limited number of experts and translators that can provide technical assistance to Chinese plants. So if there were some unexpected breakdown into Soviet plants, the Soviet experts had to fix them before being able to travel to China. And similarly, sometimes the experts were actually ready for traveling, but they had to wait to the translators that can help them. And finally, some delays were related to the fact that there was some miscommunication between Soviet and Chinese experts. For instance, in some plants, the Soviet design ended up not fitting the geolocation. There were some initial misunderstanding between the correspondence of Soviet and Chinese experts. Follow-up letter got lost, and so the design has to be redone from scratches. In 1960, the Sino-Soviet split suddenly ended the technology transfer program. This meant that the projects that experienced fewer delays had already received and maintained the planned transfer, while projects that experienced more delays were completed by China only. That tried to stick with the blueprints that the Soviets have prepared, but this project did not receive any capital goods or any technical assistance from the Soviet Union. But what I want to underscore here is that both types of projects were eventually completed and started the operation at some point. This is the focus of our empirical strategy. In fact, we will compare projects that eventually received the planned transfer, either the basic or the advanced transfer, and those are our treated projects, with projects that were eventually completed by China only without any Soviet help, and these are our comparison projects, and we know if they were supposed to receive either a basic or an advanced transfer. Putting these in a specification, a regression, meaning regressing outcome of firm I in sector S in province B at time T, on an indicator for the type of transfer that firms eventually receives and whether they were treated, controlling for industry province year fixed effect, and also a vector of project characteristics at the baseline. In terms of identification assumption, what we need to assume for estimating the causal effect of the program is that delays were orthogonal to the project characteristics or their potential success. In the paper, we ran a bunch of checks of our identification assumption. In the interest of time, I will only focus on the major ones. So first of all, we show that there are no significant differences in treated and comparison projects at the baseline. So if we look at the start year, the actual investment, the expected length of the project, these are substantially the same in number, and they're not statistically different between treated and comparison basic projects and treated and comparison advanced projects. We also look at whether the complexity of the project, in a way, could be related to the delays that they experience. But indeed, the actual number of workers, their expected capacity, is not statistically different between the two groups. And finally, we also want to check whether projects that were completed earlier and so were more likely to be treated were more connected. But if we look at the distance of treaty ports, highways, and railways, this is really not explaining why we observe these differences in the eventual probability of receiving treatment. We also show that being located in a specific industry or in a specific province does not predict treatment. One can think that some industries could have considered more important for Chinese economic development, or some provinces the same way, but indeed we don't see any significant association between being located in a specific industry and provinces and higher probability of receiving either the basic or the advanced transfer. Okay, so I have 5 minutes left, so let me move to some results. The first sets of results that we show are on the plants in the steel industry, for which we have data between 1949 and 2000. And as you can see, the firms that receive an advanced transfer had higher output, with a 55% increase over a period of 40 years, while the effect of the basic transfer were short-lived. They increase up to 20 years, 15, 20 years after the program, then they start declining, and they were no longer significant at the end of the 40 years of our sample. And we find very similar results on TFP, with a cumulative increase of 52% after 40 years since the program for firms that received the advanced transfer, no differences after 20 years for firms that received the basic transfer. We next move to investigate to what extent these results could persist over time. And what we find is that the advanced treated plants were the only one able to develop new technologies in the 60s and the 70s, when China was a closed economy. Specifically, they used two new techniques that were the basic oxygen converters and the continuous casting furnaces that replaced the Soviet machine that became obsolete. And in the long run, when China opened up to international trade, so after the 80s, these firms relied dramatically less on the import on foreign capital. They were exporting more, and they were producing more steel that was above the international transfer, the international standards, relative to plants that were supposed to receive the same transfer, but did not because of the delays. We also have some robustness checks and additional results that maybe we can discuss in the Q&A. Before concluding, I just want to shed some light on our spillovers effect analysis, in the sense that the goal of the program was creating these large industrial facilities in order to foster local industrial development. So was the project successful in doing so? First of all, we look at horizontal and vertical spillovers, and we find that both spillovers were strongly related to the presence of advanced firms. This is true for the output, like the tons of steel produced, productivity, and also the adoption of technology in the short run and in the long run. If you look at vertical spillovers, we find that there was an increase in output for all firms that were located to treated plants. This is likely because these plants were producing more than their own comparison plants. But again, we find that increase in productivity and technology adoption is only there if firms were located close to advanced treated plants. Since the 1990s, China also starts a number of institutional changes that allowed plants that were state-owned to become privately owned. And so we want to see whether there were some interaction between the technology transfer program and the privatization that happened in the late 1990s. Here we focus specifically on the period between 1998 and 2015, for which we have data. And what we find is that firms that were more productive than others were firms located close to treated advanced treated plants that became private. These firms have higher value added, productivity, they were exporting more. We also try to narrow down what are the mechanisms that can explain these results, and we are able to identify two main mechanisms. First is that so in the counties where advanced treated plants were located, there is a higher number of firms that became privately owned, and interestingly, these firms were almost all operating in industries related to the treated plants. And so we think that the increased competition may have explained why the firms that became private that could have higher productivity as they need to adapt faster to the changing market condition. And finally, we look at education, and we find that in the counties where treated plants were located, advanced treated plants were located, there is a higher number of college graduates and high-skilled workers. And since when these changes were happening, for sure, the mobility of workers in China was increasing, but was still limited and under control. We think that being able to access to higher level of human capital at the local level may have allowed the firms that became private to hire the best workers and also to have better performance. I'm out of time, so let me just wrap up. In this paper, we studied the long-run effect of technology transfer on plant outcomes. We find that receiving both state-of-the-art machinery and human capital can have long-lasting effect on plant performance, push technology upgrade, and also generated substantial spillovers effect. In terms of policy implication and external validity of our results, we think that we can say something that goes beyond the specific context that we have examined, since technology transfer programs are widely used to promote industrialization today. And in the 50s, China was an agricultural country, very similar to some African countries today that are among the largest recipients of these technology transfer interventions. I think that in terms of policy implication, there are two main takeaways of our research. First is that the effects of technology transfer cannot be replicated by imitating large foreign facilities using domestic technology, and that the on-the-job training by foreign company could be very important for the transfer of key know-how that can help the development and the success of industries. So I'll stop here, and I look forward to Rick's discussion and to your comments later on. Thanks a lot.
Thank you very much. The discussant is Richard Hornbeck. Are you there, Richard, online?
Yes, I'm here.
Okay, great. So you should be able to share your slides if you have any.
I don't have slides. I have some notes, but I'm just going to talk.
Okay, that's fine. We can see you. So go ahead. You have 10 minutes.
Okay, great. Thanks, everyone. Thanks, Michela, for a great paper. It's a really nice example, I think, to everyone about what really great research in this area would look like. I think building on a lot of the related work that Michela has done, sort of methodologically and topically. So this is a really nice paper that looks at Soviet technology transfers and sort of compares the short-term, sort of medium-term and long-term implications of receiving these technology transfers as compared to having to develop these technologies domestically. And you could imagine there could be some pros and cons where, sort of being handed something, may set you on a different trajectory than sort of having to develop it organically. And maybe there would be some benefits of, having to develop domestic capabilities and scientists and sort of doing it yourself and discovering how to do it. But it turns out that was kind of a bridge too far for Chinese scientists and Chinese manufacturers at the time, that actually, getting this leg up and getting this initial help seems to have had really important impacts. And I think I thought the most striking results in the paper were comparing and contrasting what happens when there's transfer of particular capital goods, as opposed to the transfer of those capital goods along with that knowledge, know-how, and sort of technical assistance and training. And it really seems like it's that additional technical assistance and training that's sort of, particularly important. I think I found that very interesting because I think there's sort of a general macroeconomic question that I might characterize as Lucas or others, which is this question of why doesn't capital flow to poor countries? And I think, Reka and Nico, have been working on this some with France as well, that in a sense, it's not just about getting the machine and being able to turn on the machine. A lot of these early machines, especially with new technologies that are being introduced, are complicated things. And you need the knowledge also in sort of how to work with them, how to repair them, how to advance in them. And I thought what this paper taught me really nicely, I think, in addition to maybe what some other papers have talked about, is that in being able to look at the more medium and long-term consequences, it wasn't just about machinery repair. It seemed to be actually about, 15, 20 years later, as new technologies started to become available, the paper could really nicely show that the adoption of these newer technologies is much higher when they had gotten this technical assistance. And so I think it was a nice way of thinking about how capital and knowledge are really complementary. And it's not just about spreading capital and investment and access to capital. It really is about transfer of knowledge itself. And it's a really nice application of history and being able to look at not just the short-term consequences, but the medium-term and long-term consequence over this 15-year, 20-year, 30-year, 40-year time horizon, how it's evolving, to really understand that better. I thought one interesting way to push on this, maybe if it's possible, would be to sort of explore what are the ways in which the technology in the USSR and China might have been different or might have needed to be different based on sort of different local circumstances, that maybe there's some heterogeneity in how much the way of doing things in China optimally maybe would be different than the way of doing it in the Soviet Union. Maybe there's something in the details of the steel industry and the availability of coal or metals or ores, or other types of firms where it's maybe there's some technologies where doing it the Soviet way is actually the best way to do it in China. And maybe there's some technologies where sort of not doing it the Soviet way and doing it a more organic, domestic, sort of Chinese way, might actually be better. And there could be some heterogeneity to explore there. It reminded me a little bit actually of the Ladkep and Lueck land paper on meets and bounds versus a rectangular survey system, where doing it the sort of regimented way, works well, but maybe in some circumstances where you need to adapt to local circumstances, a more informal meets and bounds system works better. And so I was wondering if there's some heterogeneity in like in some further explain the heterogeneity in the treatment effect. Similarly, I thought maybe there would be some interesting heterogeneity in the pre-existing capability in China, where like maybe in some places the Chinese scientists and manufacturers were a little bit more ready to sort of take things on, and maybe the technology was more accustomed to them, or like, and so yeah, maybe that's that idea I said about it was too much of a leap required. It was a bridge too far. Maybe in some places like they were more suited to be able to make that advance versus others. One of the things that stuck out to me about like Soviet transfer technologies is an interesting case study from the Cuban Missile Crisis, when they were building missile silos in Cuba, and they exactly copied the plans for missile silos in the Soviet Union, and it confused the CIA because they thought, well, it's clearly like they want us to know that they're building missile silos in Cuba because they made it so obvious because they copied the plans exactly, and that seems to have been like the way of doing things with these knowledge transfers. They just exactly copied it, and so. Yeah, maybe there's some heterogeneity where like sometimes copying it will work well, and maybe literally copying it won't work well. And Michela mentioned that in terms of the delays, that sometimes copying it exactly like didn't quite work well, and that was the delayed project. And so that could be some useful heterogeneity to explore. It somewhat raises a little bit of a question then about, well, is that like a problem for identification, that the projects where the technology is easily passed over, those are the ones that didn't get delayed, and the ones in which it would have been harder to transfer that technology, those are the ones that got delayed. And so maybe just digging even more into like, well, what subset of the delays do you think are more exogenous? And maybe like some of the types of delays feel a little bit more for endogenous reasons that would be related to the technology itself, or maybe you could exclude those in some robustness checks. I mean, it's a natural question of why things would get delayed, but the authors do a good job of checking observables. And to the extent that pre-trends, might be similar, they sort of do a plausible job there. I think the identification assumption naturally becomes tougher over time. But, still it's appealing that we can look at this over time and sort of see how these places were set on a different path. I think the other aspect of the results I found really interesting and striking were that it's not just a level shift up in productivity that actually sets these places on a different trajectory. Which is similar to some of Michela's other papers also, that sort of some of these programs seem to actually create like a growth innovation effect, rather than kind of like a level effect in productivity. And so I was initially sort of puzzled, like, well, why is it leading to like differential growth as opposed to sort of differential levels? But I thought the paper actually did a really nice job of sort of digging into the mechanisms there and helping to understand that, well, there actually are sort of subsequent waves of innovation and technologies that when they got this training, they were then able to not just replicate what they had done with the Soviet initial transfer capital, but they were actually able to sort of adopt later technologies also. And I thought that helped bridge the gap, a kind of understanding, well, why is there like a growth effect as opposed to just a level effect? So it's a more complicated story than just transfer of capital versus knowledge. It's like the actual transfer of knowledge shows up in that it actually fosters this later adoption and innovation, new replacement machinery, things like that. And I thought that was very interesting. The last bit that Michela sort of touched on, there's a lot of interesting results in the paper. The one that was sort of closest to my research was on the spillovers to other plants in the area, both sort of horizontally and vertically. And one interesting paper that I saw recently, I don't know if you've come across, by Giroux, Lenzu, Manji, and Mueller. It's this 2021 paper. They sort of take our $1 million plant design and they extend it through like ownership networks to other locations also. So not just looking geographically, but sort of through networks of related firms. And so I was wondering if you sort of knew something about the state level management structure of these plants and how those plants might be linked to other plants in other provinces. You might be able to kind of replicate and extend something about their design and sort of see how related steel plants elsewhere also seem to be benefiting from this knowledge transfer. And it seems to be about like the exchange of workers, the exchange of managers. And so to the extent that you could kind of dig into that being the mechanism of it's like that human capital, that knowledge that's sort of moving around those like ownership networks of firms, I thought that would be interesting. I think it's called propagation and amplification of local productivity spillovers. And so I thought that would be an interesting extension as well. But so a lot of really interesting stuff in the paper, a lot of results, nicely motivated. I guess maybe a couple of thoughts on sort of ways to maybe like sharpen the motivation and some extensions, heterogeneity. I guess it could, in a sense, there's some theoretical framework, that could be helpful for organizing the results. But I think it's even fairly clear without sort of like a formal model in a sense, but it may be just in a way thinking about, well, what are the circumstances in which this would have more of a benefit, circumstances which have less of a benefit, and then mapping that into some further heterogeneity, and like, well, which places are benefiting more, which places are benefiting less. But clearly, I mean, we're going down, if those are the types of comments, I mean, we're going down the wish list of like, all these things would be great to have, but already the paper's ticked off a lot of boxes. And it was a really nice paper. So thanks a lot for the opportunity to read it.
Thank you very much, Richard. Are there any questions from either the room or anybody online?
I have a question.
Online? Go ahead.
Yeah. Hey, Michela. So I was just wondering, do you have any result on what happened during the Cultural Revolution? Because I guess that some of these scientists were purged like by the late 60s. And so apparently, that wasn't sufficient to kill off the technology transfer.
Yeah, this is an excellent question. Actually, since these plants were very big and were considered crucial for Chinese economy, even during the Cultural Revolution, they were kind of unaffected. So there were not major manager or more educated worker dismissal as it happened in other plants. And I also take advantage of your question to clarify that, of course, these were state-owned firms. They were under the control of the government, but compared to other firms like the smaller one, they have also some autonomy. So that's why I think that the fact that they were able, we can track the fact that they were able to develop new technologies or make some hiring decision was not everything centralized and directly imposed by the government.
Any other questions? Michela, did you want to take a minute to respond to Richard?
Absolutely. So first of all, I want to thank Rick very much for reading the paper and giving us these wonderful comments. I agree that we can do more in terms of heterogeneity. We have been very cautious in doing that, mostly because for the steel industry, we only have 20 plants. And so I'm a little bit worried about any power issue, but especially for understanding which technology, like which techniques were easier to copy from the Chinese side and which ones were not. There is more that we can do, and this hopefully help us also to clarify our identification. And thank you very much for pointing out the paper on the ownership of the $1 million plants that I didn't know. Will definitely read it and cite it. And thank also for the other comments. We will definitely work on it and implement them in the paper.
Okay, thank you very much. So let's move on to our third paper, also online here.
Looks like there's just one last question.
Sorry about that. Go ahead.
Okay, thank you. I just wonder if the heavy industries had any backward or forward linkages to new private firms after the reform and opening up in China?
Yes, so at the moment we are not looking at the links in terms of managers. It's something that we have tried to do, but getting this data has not been very easy. So I'm not sure if we will eventually able to do that. That's why we mostly look at geographical proximity. So we still find that new plants that open up in the late 1990s, if they were private and located close to advanced treated plants, also have this gain in productivity that other plants or plants that were located, for instance, close to the plants that received the basic transfer didn't have. But yeah, we can expand more in terms of seeing whether there was a direct sharing of workers.
Thank you.
All right.
Thank you.
Any final questions? Okay, then we will move along to our third presenter. Michael Rubens will take us the rest of the way around the world and talk to us about management, productivity, and technology choices, evidence from U.S. mining schools. So it looks like your slides are up, Michael. Go ahead.
Okay, forgot to unmute. Okay, hi everyone. So big thanks to the organizers for a very nice conference. So this paper is about managers and technology adoption. So it's kind of established that managers are crucial drivers of firm performance, but much less is known about the exact ways in which managers affect firm performance and how they enter a production function. So the usual view in the literature, in the econ literature, when modeling managers, is that they're kind of Higgs neutral productivity shifters. So if you have a production function with output Y and inputs K and L, they kind of enter through this total factor productivity term A. Well, in this paper, I will basically argue that a key task of managers is to pick the production technology. So here in the notation of the production function is basically the function f itself is a choice of managers. And so I'm going to try to convince you later that this is not just some semantic issue, but it really touches on the core of what management is about. And it is also really important when quantifying the effects of managers on firm performance. Okay, so the concrete setting of this paper is the coal mining industry in Pennsylvania between 1898 and 1914. Why this setting? So it's interesting for a couple of reasons. So first, there is this shock to management because of the entry of mining college graduates in managerial positions in this industry. So in fact, I observe throughout the panel, I observed the first entry of managers who graduated from mining colleges with mining engineering degrees. So there's like this gradual professionalization of the management of these mines. And so the share of mines in the data set with managers who obtain a mining engineering degree increased from none to 4% in 1930. Secondly, it's a time period with extensive technological change. So as we already saw during the earlier presentations, so electrification was an important innovation. And so also in the coal industry, you see this happening, especially in terms of the automation of the haulage process. So, in order to operate a coal mine, you need to do three things. You need to first access a coal bay, then you need to dig out the coal, so you need to cut it out, and then you need to get it back to the surface, at least if you're operating an underground coal mine, which will be the case here. And so I will mainly focus on the automation of this last step, so the haulage of the coal to the surface. Basically, before it used to happen with mules, then starting around the 1870s, there was an increased adoption of steam locomotives. And then throughout the panel, so throughout the time period I'm observing, there was basically a replacement of steam engines with electrical engines and compressed air engines to haul this coal to the surface. And so I will explain this later why this is important. And a final reason why this is an interesting industry to ask this question is that basically it's kind of a stylized setting due to the fact that, so I'm going to look at anthracite coal, which is nearly homogeneous product. And so it's a stylized setting because firm performance will basically boil down to productivity here. So I will just be able to be very precise on what firm performance means. So it will just be quantity productivity difference between mines. Oh yeah, so the question is, well, we see the entry of these new types of managers. How do they differ from other managers in terms of the total factor productivity of the mines they managed? And how do they differ in terms of their choices of technologies? Okay, so in terms of the data, so I'm going to combine two data sets. So first is I rely on reports, so inspector reports from the Inspector of Mines in Pennsylvania, which gives you mine level production and cost data. So it's going to give you output and inputs in quantities. So in terms of inputs, it's like labor, intermediate inputs, and then the different technology types. So I'm going to observe whether they used any locomotives to haul coal to the surface or not. And if they did, what type of locomotives they use. And so this information is available for all the 582 anthracite mines in Pennsylvania throughout the time period. Secondly, I also observed in these reports the names of the managers of these mines, and I link these names to both population census records and mining school alumni yearbooks to know, well, actually more general, so alumni yearbooks of all the colleges in the United States, to know whether these managers obtained any college degree, and if they obtained a college degree, whether it was in mining engineering or in some other subject. Okay. So I'll be brief on the literature. So I build on three classes of literature. So first, there is very large literature on measurement and productivity, and as already said, I contribute by moving away from modeling managers solely through the black box of individual productivity. Secondly, I contributed to this historical literature on the effects of higher education on both productivity and innovation. And so here, the difference with this literature is that that literature is mostly on invention, and so on how educational change affects invention, while we'll focus on the adoption of new technologies rather than their invention. And then thirdly, there is literature on the role of engineers in shaping industrialization. And so here again, most of the literature really views engineers as inventors, while I will focus on engineers as adopters of technologies. Yeah. So let me show you the technological change. So by the year, so this shows the total number of locomotives used in the anthracite mining industry in Pennsylvania by type of technology. So you see that in 1900, the dominant technology was still steam technology, right? But one of the nasty things of steam technology in coal mining is that usually you have mine gas in coal mines. And so if you use steam engines under the ground, it really risks blowing up the entire mine. So for that reason, there were two new types of locomotives that were developed. One was electrical locomotives, so they were propelled by electrical engines. And then a second was compressed air engines, which were which used air compressors. And so both of these technologies were much safer to use under the ground. And you see that for the first 4 to 5 years, both technologies grew at about the same rate. But then after a couple of years, it really became clear that the electrical engines were the better technology. And so there's also a lot of engineering reports on that. And so by around 1910, electricity overtook steam technology, and electricity really became the dominant technology. Okay, so in terms of the empirical analysis, I'm going to do two things. So first, I'm going to examine the effects of mining college graduates as being managers on total factor productivity, conditional on all the other inputs, so including the locomotives. So I'm going to keep the locomotives and all the other inputs fixed. I'm going to see whether managers shift the production isoquants. And so, of course, in order to do that, you need to account for endogenous input choices. So that's a well-known issue. And so I just rely on timing assumptions as is usual in the IO literature when estimating production functions. Secondly, I'm going to look at the effects. So I'm going to look how mining college graduates differed from other managers in terms of which technologies they use. So I'm going to coin this the indirect effects on productivity, because now I'm not going to keep these locomotives fixed, but I'm going to allow them to change depending on which manager you have. So this is basically going to amount to estimating the input demand functions for each locomotive type and to let them vary with the type of manager you have in the market. Let me first show you the results for the production function. So in terms of notation, so I have mines I who produce a tonnage of coal Q in 30 UT, and then I have labor intermediate inputs, that's meaning black powder, the three technology types K, which will be dummies, managerial characteristics X, and then some time trends. And so what I find is that basically when I estimate this production function, I find so controlling for all the other inputs, I find no positive effect of mining college graduates on outputs. So I even find a negative coefficient, but it's not significantly negative. So the standard errors are kind of wide, like always with production function estimation, but so it could still be that there is some neutral productivity gain from using a mining college graduate, but it doesn't seem very likely, and the effect is going to be small. Now, another thing to note here is that when we compare the two new technologies, so electrical engines and air locomotives, which were the two technologies in which I see basically changes on the intensive margin throughout the time period is basically the electrical locomotives were the better technology. So that also squares with engineering journals at the time who were describing that these electrical engines were the better technology. Then secondly, so I look at how these different usage of these different technologies differed between mines that were managed by these mining engineers and by other managers. So I just estimate, thanks. So I estimate a fixed effects regression in which I include these mine fixed effects, and I check out these technology choices different between managers. And I find that these mining college graduates were 20 percentage points more likely to use electrical locomotives than the other managers, but this doesn't apply for the other two locomotive types. And so in terms of relative effect, this is so they were almost half as likely to almost 50% more likely to use electrical locomotives than these other managers. Now, of course, there could be other omitted variables that are that are varying over time that are not captured in these mine fixed effects that drive both the arrival of these engineers and of technology adoption. So I address this in two ways. So first, I do an event study by looking, well, is it the arrival of the mining engineers that is followed by these the adoption of these electrical engines, or is it the other way around? When I do this, I basically find that it's mostly these engineers arrive, and afterwards you see adoption of electrical engines. Now, this is still, so you could still come up with a story in which the owners of these mines anticipate wanting to electrify their mines, and because of that, they hire engineers. So is it that story, or is it rather the engineers who took the initiative themselves of electrifying these mines? So for that, it's kind of hard to econometrically distinguish these two stories. So what I did is I basically looked for anecdotal evidence from contemporaneous reports, and they mainly suggest the latter. So for instance, I have this quote here. So the directors of these mines were not experienced in mine development, and so hired experts who were. And also the managers faced uphill battles of educating the officers and the board, so they had context to understand the reports on locomotive adoption to them. Second is that, so this is from Spence, this is on copper mines, but so not on coal mines, but you could expect that it was similar. So basically, the important thing was to convince mine promoters and miners that scientific methods were superior and that engineers should supervise every step in the production process. And finally, so this is a coal mine in Pennsylvania. And so this is a contemporaneous report saying that these engineers were planning on installing new types of locomotives. So tandem locomotives are basically jointly using electrical locomotives with other locomotives. So this all suggests that it's really the mining engineers who took the initiative to adopt these new technologies. Okay, and then now, why do we care about this? Well, this has really important implications for measuring the returns to management. So if we control for all the technology choices that are made, like we usually do when we estimate a production function, so these technology choices would turn up in the capital stock, then I find no effect of mining engineers on total factor productivity. But once I account for the fact that these managers select different technologies, I can calculate the unconditional effect of these managers on productivity through technology choices, and I basically find that that the average mining engineer increased productivity on average by 3%. So that's at the average mine. So even though I don't find evidence for a direct effect of these managers on the output quant, they did select different production technologies who had an effect on the output quant, right? And I'll conclude. So I have some things on mechanisms. So basically understanding why these managers were different, but I refer to the paper, so I don't have time to cover that here. So basically to conclude, so I study professionalization of management in US coal mines during the Second Industrial Revolution. I look at the entry of these managers with engineering college degrees, and I see that the main dimension in which they differ from these other managers is the technology choices they made. I find that their main effect on productivity was also through these technology choices. And a more general takeaway from the paper is that when quantifying the effect of managers on productivity, it's really crucial to acknowledge the fact that contrary to other production inputs, a key feature of managers is that they make active decisions. So for instance, not only on technology adoption, but also on export decisions, R&D investment, human resource practices, etc. And so when these decisions already turn up in the production function, it's really important to allow for these managers to make these decisions and to take this into account when measuring the effects of managers on productivity. And I'll end there.
Thank you very much, Michael. So our discussant is here in the room, Michael Andrews. Go ahead.
Thank you, Michael, and nice job, Michael. And I am Michael. Pull up my slides here. So wait. This is not Acrobat. Full screen, please. No, that's all right. Let's just run through these like this. Can you see this okay on Zoom? Oh,
not yet.
No, my bad. This one's on me. Yeah. Just trying to remember the words of Peter Meyer. Yeah. Just trying to see where did my slides go. There we go. Okay. To share. The green one. There you go. UMBC doesn't use Zoom, so I'm actually out of practice. And my slides are right here. Okay. Thank you. Sorry about that. So thank you all for sticking around to the end. Michael's paper was the last paper in the last session on the last day, and I am the discussant for that last paper. So I think that makes me the grand finale of the entire EHA meetings. So I am deeply humbled by that honor. Also deeply humbled to discuss what was a really interesting paper. So thank you again to Michael for that. As you just saw, the question Michael's trying to answer here is, do college-educated mining engineers, and actually we can be even more precise than that, we can say, do college-educated mining engineers with degrees in mining engineering improve the productivity of Pennsylvania coal mines from 1898 to 1914? And this is a fascinating industry and a fascinating time period, but I think this paper is even more interesting because it's really getting at two deep fundamental economic questions. The first of those is just, what is the role of management in firm productivity? The second, which I think is also quite important and interesting, is what is the role of education in managerial ability? Why would we expect mining engineers, people with mining engineering degrees, to make better managers maybe than other types of education? So maybe that question sounds obvious to you. It's not obvious to me that that's such a trivial issue. Right now, the paper is very much structured to think about the role of management on productivity, thinking about the introduction of college-educated mining engineers as a positive shock to managerial ability. But I think that we can think about this second issue as well, and there's quite a lot to do to think about that's interesting on that dimension too. What does Michael do exactly? Well, he talked about it very well, so I won't spend a lot of time on this. You saw a production function, and the typical approach in studies on do management matter is to look at how this TFP term changes with managerial ability, right? So shifting our production function up and down as our managers are more or less skilled. And Michael's big insight, which I think is correct and important, is that, of course, managerial skill can also affect the input mix, right? So the inputs that we choose can also depend on managerial ability. And if we just looked at this Hicks neutral component, what Michael calls the direct effect of management, we're going to really understate the total effect of managers. So let me try and summarize his results maybe a little bit more compactly. So what he finds is that managers with mining engineering degrees actually decreased TFP by about 4.5%, right? So if we just looked again at this this A term, this is negative 4.5%. Now, it's not statistically significant. It's imprecisely estimated. We can reject large increases in TFP from these mining engineering degree graduates. Of course, again, the interesting part, the innovation here in this paper is to think about the indirect effect. So as Michael shows, it's these college-educated, mining engineering degree-educated managers who are much more likely to adopt the most productive technology, in this case, electric locomotives, about 50% more likely. And if we look at these direct effects, if we weigh the probabilities of using different technologies and the productivity increases of those inputs, we find that this indirect effect increases output by about 3%. So if you add these things up, we get 4.5% minus 3%, it's minus 1.5%. So even on net, we still can't reject the fact that managers had actually zero effect on output or productivity. The point estimate is negative, but again, small and imprecisely estimated. We can reject that managers are having a very large net impact on productivity, which is interesting, a bit puzzling, but interesting. And I mean, Michael's bigger point is that if we just looked at this direct effect, we're really understating what managers do, and the effect looks much more negative than we find. So as you could probably guess, I mean, as you saw from Michael's presentation, and even if you didn't see the presentation, you just looked at what he's trying to do. To think about these estimates, we need to use some really cool data, and we certainly have that here. So we have data from annual report on the Bureaus of Mines and mine inspectors, which gives us locations on, I saw 604 in the paper, 582 in the presentation, about 600 Pennsylvania coal mines. We see the output from these mines. And what's really neat is we see the technology choices of each of these mines, so the locomotives they use. And what's also really cool is we see the names of the mine managers, which opens up a lot of possibilities. In particular, we want to figure out something about the education level of these managers. So what Michael does here is links these to different sources, links them first to the decennial population censuses, and then from there goes to Ancestry.com and tries to find alumni lists for different educational institutions. And also there's some in the paper about really trying to understand what does that education look like. So actually going and looking at course catalogs for these different degrees to get a sense of what they're actually learning. I will say it was a little opaque to me as a reader how exactly this matching to Ancestry occurred, and exactly which records are being matched to and how to think about unique names and things like that. So I think a little bit, maybe significantly more discussion there would be useful. I should also say, while the data was cool and really neat, there was maybe not a ton of it, right? So in total, we've got only about 300 managers. Not a lot we can do about that. Only 17 of these people are actually linked to a college degree program in mining engineering. And I should say also there are more mines than that in the data. Many of these managers are operating multiple mines. This is the list of schools Michael's linking to. And again, Michael, correct me if I'm misunderstanding afterwards how this linking is taking place. As I read it, he's looking at these records for, I think this is 15 schools here. He has alumni records from some years for some of these schools. My concern is that we know this is not the universe of mining engineering programs in the U.S. So this is a snapshot from the Commissioner of Education reports in 1910. What's so cool about the 1910 report, as far as I know, this is the only Commissioner of Education report that breaks out student counts by college major. So we can actually see mining engineers here. And there are many more schools than show up in Michael's data there. So, I guess we can even drill down and look at like course catalogs for some of these schools and see exactly what the curriculum looks like. It looks quite similar to the schools. Michael's sample. I won't spend time on these pictures from Iowa State. And I guess my concern, why this might be an issue is, if we have these mining engineer, college educated individuals who we're not linking to in the ancestry records, they show up as non-educated people in the data. If we think that's like classical measurement error, it's not surprising that maybe we see these effects that are close to zero, slightly negative, imprecisely estimated. So to the extent that we're not actually seeing the universe of college-educated engineers, we're just treating as treated a small subset, that could potentially be an issue. I think, obviously my first instinct as an economic historian would be to say always go and collect more data on additional alumni lists. As someone who's done some work with yearbooks and alumni records, I know it's difficult. A lot of them aren't on Ancestry, so I'm a little bit skeptical that you might ever be able to fill in all those years. My instinct, and you may disagree, but I wonder if maybe it would be possible to set aside these fantastic micro data on the identities of the managers and take a more reduced form approach. Maybe think about distances to local mining college, whether that shows up in your productivity estimates in any way. So that's something you may want to consider. On my last point, I have just a couple minutes left, but I said at the beginning, I think one of the things that's really cool about this paper is it gives us a way to think about why does education matter for productivity. Obviously, there's been a lot of people thinking about why does education matter. As Michael pointed out in his slides, a lot of work, including some by Michela and myself, has thought about how does education improve innovation. Much less thinks about how does education affect the diffusion of ideas and the ability to adopt new ideas. And I think that's really, really important, right? This is like the golden cats race between education and technology story, right? Do we have enough people who have a baseline level of knowledge to take advantage of new technologies as they come online? If we do, then the college wage premium will be relatively low. If we don't, that wage premium will be relatively high. So we have some aggregate studies about these questions, but I think having good micro level empirical evidence on the role between education and diffusion is something that really we don't know a lot about and would be really good to know about. So I think this paper is really interesting in that dimension, and I think potentially you could do more about thinking about how does education actually affect managerial ability, right? So you could ask about does the specificness of the education matter? You're already in the study comparing people with mining engineering degrees to other college graduates. I found that comparison really interesting. Is a mining engineering degree better than other kinds of engineering? Since we're thinking about the adoption of electrical locomotives, maybe electrical engineers would be interesting. And you could even think across mining programs, different programs focus on different types of skills. And these things might really be interesting to focus on, either here or maybe in future work. You might also wonder whether the trajectories for people with different kinds of education are different, right? So one thing that jumped out is these mining engineers these people with mining engineering degrees tended to be younger, so maybe they're experimenting early in their careers and then productivity will grow faster. So I think all of these things potentially one could look at. The limitation, I guess, is just the richness and the statistical power from the data on mining engineers, but I think there's a lot of really cool questions that we're able to get into with this data, and hopefully is really exciting. So once again, thank you to Michael, and thank you all for sticking it out to the end. Thanks.
Okay, we have a couple of minutes for questions here. Are there any questions either here live or from anyone online? I don't see any right now. Michael, did you want to respond at all? You have a couple minutes. You could take the last couple minutes.
Yeah, thanks. Yeah, so thanks a lot, Mike, for a very good discussion. I wrote down the comments, so I'll look at them more in detail. Maybe one thing on the mining school list. So the total set of mining schools I matched to is much wider than the ones that are listed in the ones on which I have the directories which are in the paper. So these were mainly used to look at the curriculums, but the total set of mining schools is basically all the mining schools that are on Ancestry.com, plus the ones that I have the alumni list from. Now this may still not be the universe, but so yeah, I'll look into that to see like what percentage I'm matching. So
yeah, I would actually recommend bragging about that quite a bit more in the paper. I think digitizing and using a much bigger set of these yearbooks is a pretty impressive contribution in its own right. So I would pat yourself on the back a little bit more in the paper.
Thanks. Yeah, and then I'll keep it at that. So again, thanks a lot.
Anything else? We are running up against our time here, and I know there was a flight brouhaha here, so a lot of people have to leave to rearrange flights. So since we're up against the end, I just want to thank everyone for both virtually and in person for the session, and a last round of applause for all of our speakers and our discussants. Thank you very much, everybody, and have a pleasant rest of your day.